Hi guys, Professor Doney here, as promised, putting together some quick short videos for you to cover chapter 13 and just a little bit of intro into 14, which we would have done on class this past week. So as you go through these, I recommend you look at also the lecture notes that are online, and that'll help you get through this. Not a lot in chapter 13, just going to do a little bit of definition, a little explanation, and what problem you need to be concerned about. Alright, so chapter 13, we are talking about temperature. Okay, temperature is defined as the hotness or coldness of something, but that really isn't a very scientific, because what may be cold for you, it may not be cold for me and cold for someone else. So that's more of a relative preference kind of thing. The definition we're going to use as scientific is it's equal to the average internal kinetic energy. Now we learned in chapter 6 that kinetic energy was 1/2 mv squared. So what this is really saying, if you could find the average internal kinetic energy of all the moving molecules of that material at their speeds, you would get a quantitative measure, meaning a numerical measure, and we call that temperature. So obviously something that has a higher temperature than another, or twice as high, would have twice the average internal kinetic energy. All right, but we still look at it as hotness and coldness. A couple other definitions. Thermodynamics. Thermo is short for heat or temperature. We talked about dynamics in chapter 10, that's moving. So this is really just the study of change in heat, temperature, things like that. Okay, it's a pretty wide topic there. Weather, cooking, all that kind of stuff. Thermometric properties, again, there's that heat or temperature properties, are properties that change with a change in temperature. Okay? And the most common one that we see is usually when we heat things up, they tend to expand, and when we cool things off, they tend to contract. Okay? And there's a whole section here in chapter 13 that talks about that. We use that idea in determining how concrete will expand in the heat and contract in the cold, and why they put in expansion cracks, things like that. Same thing with bridges. So another definition there. So thermometric property. Another example would be changing in color. There used to be shirts that were popular back in the 80s that if you wore them outside, they're one color, and went inside where it's warm, it turned into a different color. And now they use this basically on those strips for temperature. They can put on your forehead, and they change color based on the temperature. Now the idea is we use this thermometric property to look at building an actual thermometer, which is what we need to do for this semester, this class year. If we use that idea with fluid, and we putting it at the freezing point, and then we go and take that fluid all the way up to the boiling point, what we see is the fluid will expand as it's heated and contract when it's frozen. And then we can go ahead and we make graduations along there, meaning lines or levels, depending on how many we make. If we're using Celsius or centigrade, there is 100 of those divisions. If we're using Fahrenheit, there's 180 of those levels. So in the older days, before digital thermometers, Fahrenheit was actually more accurate than centigrade or Celsius, because there's more levels that you could measure to. But now with digital, it really doesn't matter. Okay? Now I'm going to run out of room here in this video in a moment, but we'll add a second one about how we come up with converting from Fahrenheit to centigrade and vice versa, and it comes off of this. But we'll start it here. We have 100 graduations for centigrade, 180 for there. Boiling point for us in Fahrenheit is 212, freezing 32. And over here, freezing is 0, boiling is 100. Okay? Now we could make up any scale and call it the Physics 101 temperature scale, and we'd have to have a freeze point, a boiling point, and how many levels in between. So we're going to continue with this. And